Hello everyone, today we are going to do a PID control tutorial together. Let's look at this example showing on the slide. Design a proportional type controller. Design a proportional type feedback compensator that is CS equal to A, to the system depicted below using a linear log paper. Ensure a phase margin phi m equal to 45 degree. Calculate the approximate of the setting time, that is T control. Finally, by using the designed controller gain, provide the closed loop transfer function. By applying the final value theorem, calculate y infinite if reference signal is given as RT equal to 3 multiply 1t. So let's begin with the solution. The open loop transfer function of this system is G open loop equal to CS multiplied by GS multiplied by SYS. That is CS equal to A multiplied by 10 over 0.1s plus 0.5 multiply 1 over s. So let's assume A equal to 1. That is G open loop equal to 0.1s plus 0.5 multiply 1 over s. Rearrange these functions, we could get 20 over s multiplied by 1 over 0.2 s plus 1. That is two systems. One become one TP system and another is 0TI system. So let's now draw the board plot. First, we draw the sketch in a blank paper. So as we have learned before, the 0TI system, the cutting frequency equal to AI equal to 20 here. So this is 20. The slope of these lines is minus 20. and the frequency plot of one of a zero TI system is showing us here. And for the 1 TP system, the cutting frequency equal to 1 over T equal to 1 over 0.2 equal to 5. So that is 5. It's cutting frequency. And also the slope of this line is minus 20. This could be. And let's look at the frequency plot. The 1 TP system So what we need to do here is to merge these two plots together. So if we look at this, these two plots, one and two, let's merge it together. Before the frequency less than 5, the line, the merged line should be this, and after 5 the slope become minus 40 because this line is minus 20 and this line is minus 20, and we merge these two lines, the slope become minus 40. And if we looking at the frequency plot, begin with minus 90 degrees, this is the plot 3, and this line is the plot 4, this one is plot 3. We merge it together. This blue line is what we get at the end. So it's just a sketch to show how to draw the board plot. Let's use the linear log paper to draw this diagram. So here is the linear log paper. As I sent to you before, and I think you should have this one. And with this paper, you can join the board diagram, and this axis you can arrange it with the needed scope. So this scalable X. So here we need 5 and 5 and 50. So let's make this multiply by 10. It becomes 50, and it's 5, and it becomes 0.5. This is 2, and this is 20. This is 0.2. And Here you can arrange the two diagrams together. And if you look at here, what we use is 0 to 40. So let's make the top with 40, and so this each grid become 2 here. So let's draw the first diagram. Here is 20, here is 2, so the slope is minus 20, and we straight these 3 points. That's the first plot. And let's begin with the second one. The cutting frequency is 5. Here's minus 20. So this is the second one, and we merge it together. From 5, the slope become to minus 40, and if the slope is minus 40, and when you reach the omega equal to 50, and the amplified volume should be minus 40. So the blue line is the final diagram of amplified, and now we begin to draw the frequency diagram. Let's make each grid with 45 degree. This is the third plot. Sorry, this is fourth plot of the 1TP system. The slope is minus 45 degree per and this line is the 0TI frequency plot. This is 1TP. And if we merge these two together, it should be from the minus 90 to minus 180. So now we finish the board diagram, and let's go back to the questions. With the phase margin phi m equal to 45 degree, so the phase margin is the side off from the minus 180. And if we look at this diagram, the phase margin equal to 45 degree, we can find this point. With the accordingly the frequency equal to minus 135. And if we go back to the amplified diagram, here we can find the point, and the frequency here equal to 5, so we can now write the frequency equal to 5, and if we calculate the we can find the measure of shift is 12 dB. And let's go back with the calculation. So when the phi m equal to 45 degree, the cutting frequency equal to 5 radians per second, and with the function t control, which is the setting time, is bigger than p over cutting frequency, less than 3p over cutting frequency, and we calculate the number. You can get this setting time is bigger than 0.63 seconds and less than 1.89 seconds. And we get the measure of shift x equal to 12 dB, and then we have this function 20 log a equal to minus x. So the 20 log a equal to minus 12. So the a equal to 10 minus 12 equal over 20, which is 0.25 approximately. So with this CS equal to A equal to 0.25, so the open loop transfer function equal to s 0.25 over s multiplied by 20 over 0.2 s plus 1. and that's equal to 0 to point, that's equal to 5 over ice multiplied by 0.2 ice plus 1 divided by 1. And then the closed loop transfer function equal to Cis multiplied by Gs over 1 plus Cs multiplied by Gs multiplied by Sys. That is 0.25 multiplied by 10 over 0.1 s plus 0.5 plus 1 over s multiplied by 0.2 s plus 1 divided by 5 . So we rearrange these functions. We can get 0.2 s squared plus s plus 5 divided by 5 multiplied by s. And we have this reference signal RT equal to 3 multiplied by 1t, and we apply the Laplace transformation on these signals. So we got the Rs equal to s divided by 3. And now we calculate the final volume using the final volume theorem. The final volume equal to when the t approaching infinite, the limit yt, that's equal to when the s approaching the 0, the limited s multiply ys, that's equal to ys equal to the closed loop transfer function multiplied by rs, that is 5s over 0.2 I squared plus s plus 5 multiplied by 3 over s. That is 15s over 0.2 I squared plus s plus 5. When s approaching 0, that volume equal to 0. So the final volume of this system is 0.